I reach this part, I will start with an outline of the presentation. So, well, in the beginning, I'm going to talk about the thermodynamics and the kinetics perspective on biomolecular structure prediction. Well, I will talk a bit about, from the structure prediction point of view, what the challenges are, and also how molecular simulations can be used as a quantitative atomistic microscope. Of course, talk a bit about the strength and the deficiencies of molecular simulations, and then carry on to the essential part of how to use basically molecular simulations in such a way that we incorporate experimental data for say a particular system of study, and in the end of the day we're able to get a system specific, we can call it well, top down, because we're introducing experimental data from above, if you wish, to the structural ensemble, but also it's a bottom-up approach because we are using a force field. So thereby we're relying to first principle based type of configurations. So that's how we see basically incorporation of experimental data into molecular simulations as a system-specific bottom-up and top-down approach. So I'm going to talk about a bit configuration reweighting. So this is one way to introduce experimental data into molecular simulations and then get posterior ensembles, but also talk about the very essential part of this study, which was path reweighting. Okay, so well, I'm super convinced that I don't have to persuade people about why protein structure prediction is important. And why actually proteins are important. They do participate in key functions of the cell, and such, for instance, in ion channels, enzymes, or they can be well, misfolded and form and cause diseases like misfolding diseases, and such a function depends on the structure. So it's really crucial to be able to get the structures right, and this means both in atomistic resolution, but also in a quantitative manner, and also not only having the ground state structures right, but also have low populated structures right. But of course, if you were to ask perhaps experimentalists, well, they often uncover a single ground state structure. So for instance, think of X-ray structure determination. They rarely report important but yet intractable excited state structures. I mean, there have been advances in CPMG and MR, for example, that they can also talk about low populated structures. They rarely report how these structures interconvert with each other, and more importantly, and this is a big challenge we're facing now, is that they experimentists frequently fail to address the heterogeneous structural ensembles at play. But of course, in reality, and from thermodynamics point of view, well, we do have, so matter exists in an ensemble of microstates specified by given conditions. For instance, if you have a constant temperature, pressure or volume, and number of particles. So, I mean, you do have an ensemble of configurations. So this single structure picture fails to address this ensemble thermodynamics of the system. And of course, moreover, so this is an extra layer of complexity. Of course, structures so states or structures, or they interconvert with each other with a particular time scale that is dictated by these transition state regions. And this was famously celebrated in the 30s by the TST. So this single structure picture really also fails to address the ensemble of pathways now of the system. So we really need well, tools to address this. And here, this is another picture of how we actually, so matter exists in a more of a form of a structural ensemble rather than a single structure. So you have several minima along a protein folding pathway, and you have a time scale of interconversion between states. For instance, consider these three states. You have the thermodynamics, which is the populations, but also you have an conversion time scales. However, often experimentalists, they do find a superposition of such structures, each of which exists within their own weight. So you get a blur picture or a blur signal, or a low signal to noise ratio, and this is exactly the reason that this happens in experiments. But of course, I mean, experiments can be very helpful into determining the structures of, or structural ensembles, perhaps, of proteins. Here we name a few, but also they face systematic and random errors. I mean, here to name a few, the fact I already mentioned that we have an ensembled average data, or the fact that we can only monitor a few properties or a few observables of the system, and this is the sparse data problem, and of course the random and systematic errors of the measurement. Another approach to try to basically determine structures or structural ensembles is molecular simulations. And here I don't really have to go through the detail, but given a potential energy function, which is sort of a bottom-up view on the problem, so we basically describe the system or the interactions of a system by interactions of a kind of bonds or dihedrals that come out of ab initio calculations or quantum mechanical calculations, and also parameters, for instance, in Lagrange that come out of well, say, vaporization experiments. So given that potential energy function, we're able to get a structural ensemble. We are able to get in good resolution structures, populations, which is the thermodynamics, but also the interconversion timescales. But the problem here is that, well, first of all, well, force fields are problematic, and moreover, the fact that you know, we have a general force field for all folded proteins often fails to capture, for instance, the thermodynamics of a given range of proteins than others. So these are general force fields. So what we do need actually is a system-specific sort of system-specific microscopic ensemble that adheres to the experimental data. And we need that structural ensemble to very well reproduce both experimental data regarding the thermodynamics for that system, but also to reproduce the proper kinetics for that system. So we really need ways to incorporate both thermodynamic and kinetic data into the structural ensembles. And now I'm really cutting to the chase of the study, where it's basically, you know, a very well-known way to do these type of reweighting of your molecular dynamics ensemble. Is the maximum entropy principle. So we can always reweight microscopic ensembles to match specific system-specific experimental data. For instance, consider that you have a prior distribution, and this is your as a function of some collective variable, and then you basically, well, your ensemble average along that of that variable is basically given by S0. But say, for instance, that you have some experimental data, for instance, RDCs, or even, if you want, electron density maps. So that your average electron density, and consider this being the electron density variable, is a bit shifted to the right. So basically you need a way to reweight your prior ensemble so that you move to a different distribution where the average basically is as dictated by the experimental observable. So maximum entropy is able to, the maximum entropy principle is able to do that. It provides with a posterior ensemble that is maximally close to the experimental data while minimally perturbing the prior ensemble, which is basically your molecular dynamics ensemble. Fine, but this is of course this holds in configuration space, but it also holds in the path space. And in the path space, what changes is that instead of defining your space is just defined, instead of coordinates, it's defined on pathways. So so far the kinetics Kinetic experimental data have been very difficult to incorporate in molecular dynamics. And basically, I'm going to be showing you later a way to basically try to approach, to solve this problem. But we start from the reweighting procedure for in the configurational space. So consider that you have a prior distribution px, then what you want to do is basically to reach to a new distribution, a new distribution px given your prior distribution p0. You want to reach to a new distribution px that whose ensemble average properties reach an experimental average, and also it's normalized. So the way to solve this variational problem is by maximizing the entropy. So this can be very easily done by the usage of Lagrange multipliers. Yeah, so this has been done so far by several people. But here, for instance, we show how this is done with, so for instance, this is from a review of Andrea Cesari and Giovanni Bussi, where they've used Lagrange multipliers to meet a particular experimental observable. And then they basically find that their posterior distribution is proportional to the prior distribution times an exponent of the Lagrange multiplier, so times the observable. So in other words, consider that you have your original free energy here, whose basically original average is dictated by this gray line. Basically, you solve the Lagrange multiplier constraint problem, and then you get basically a new value that is linear on your S variable that tilts the original free energy to a posterior free energy here, which is this one, whose basically average is the same as the experimental average. So far, so good. But so basically, and I'm reaching to the part with what we did. So basically, we followed the same approach, but now we define our probability distribution in path space. So basically here is the very same, and this is, we're using the maximum caliber. So maximum caliber is basically the maximum entropy principle in path space. So we really, this is the same formulation. The only difference is, so basically we want to restrain to an experimental observable. This experimental observable is the rate constant. The rate constant depends on the ensemble of pathways rather than the ensemble of configurations itself. And that's why basically we need to resolve to the maximum caliber that is defined in the path space. In the end of the day, we have our prior distribution of pathways that we reweighting using this reweighting function. And our method basically is all about how to find this reweighting function f. Okay, so consider now, but to do that, we need to have a forward model. So this means that if you want to restrain, say, to a rate constant, KAB, you need to express the rate constant as a function of the path ensemble. So this is how we do it. This is nothing but the flux out. So consider a state, so the rate constant to go from A to B. This is nothing but the flux out of state A times a conditional probability to reach state B, given the fact that you just exited state A. And basically, so in our forward model formalism, we forget about the first term, and the second term basically is this one. So it's all about how to change your conditional probability distribution as a function of the pathways. So this is the bottom line of the approach, by basically finding this function f. So I'm going to be explicit. So in a parallel with the maximum entropy work by the Lagrange multiplier work by Bussi, here we, as I said, multiply our prior distribution of pathways with this term, f of x. So first, we need to find our Lagrange multiplier. So imagine that you have an AB, so an experimental KAB, and you have your prior KAB that comes out of MD. Then your mu, your Lagrange multiplier, is nothing but, well, you take the ratio and then you take the log. So this is your Lagrange multiplier. Fine. Then basically we show in the paper that this function f that acts on the pathway, so this weighting function, is really related to the committer function. So if we want to find the f function, we really need to find the posterior committer function. Now, what is the committer function? So imagine that you have trajectories that are leaving state A, and these you can always plot a probability distribution, a configuration probability distribution of these trajectories. The committer is nothing but, well, basically the probability of the probability density of trajectories coming out of state B divided by the probability density of trajectories coming out of state A and B. So this is what the committer is, and this is the prior committer. And now, given the fact that we know our Lagrange multipliers mu, we are able to find what is the altered committer, so the posterior committer. And I will be showing an example in a moment. So given the fact that we do have our posterior committer, we know how the committer changed due to the fact that we changed the rate. We've found that there is a self-consistent way to relate this posterior committer here and the respective configurational density to a path, sort of a path-dependent function f. So this is an iterative way to find what the function f is. So consider now I'm going to the examples. So this is how the f function looks like. So you have a stable state around here, state A is here, state B is here. So by solving this equation, you're able to have a CV dependent function, which we call it a kinetic path reweighting function. So if you're leaving state A and you're going towards B, then if your pathway reaches, say, this point, then it gets a weight of 1.1. If it maximally reaches this point, it gets a weight of 1.2, and so on. So for instance, consider you have this red pathway. So since at this value of L, since your pathway reached maximally this value of L, then you go again to your f function at this value, and this is basically the new weight that this pathway should take. Now, so this is how the path reweighting works, and in a pictorial way, we have. So this is basically you have your molecular dynamics, then you reweight to get equilibrium, prior distribution, and then you reweight with the path reweighting function, and here, basically, I'm really closing. So you have your prior. So this is a problem of protein folding problem where you have your prior distribution for the committer. This is how your posterior committer looks like. You're basically constraining your simulation. You're trying to impose a slower folding rate. So basically, your posterior committer shifts. From this posterior committer, you're able to find a path reweighting function that looks like this red curve. And this red curve, this path reweighting function alters your conditional probability. So this is a log conditional probability. So this gets slower. So your conditional probability is lower. And this is a fact that you're imposing a slower rate. And then, and this is a crucial and final plot, is that your original distribution, so this is a free energy, and this is the folded state is, sorry, the unfolded state is here, the folded state is on the right. So basically by imposing a slower folding rate, you're essentially increasing the barrier, so in red, but also you're shifting the barrier towards the right. So basically this is the free energy. So this was the original as a function of the contact. So this is the folded, this is the unfolded. So basically you are shifting your transition state to the right. And this is the model we've proposed for alanine type peptide. Basically by imposing a slower rate and using our protocol, you're getting a shift on the transition state to the right, but also a higher barrier. But that I want to thank, because I think I'm out of time. Well, basically to conclude, we do now have protocol that uses the maximum caliber to reweight continuous pathways to adhere to kinetic, so rate constant constraints. And this is a general approach, it can be used to many different systems, and we're now exploring the possibility to correct basically the potential energy surface of the force field rather than reweighting the ensemble of pathways. So this is an ongoing work. With that, I want to thank my collaborators, Pierre Bolhos and Michele Vendruscolo, other long-term collaborators, my funders, and you for your attention.